one. Yeah. I thought about rewrite that. It's a 1. It's a 1,413. Get it yet? Okay, so how are you going about solving for it? How are you going about solving for it? Because 2 different ways. What?
Law of sines and law of cosines.
Okay, so law of sines. And what does alpha turn out to be? And then law of cosines. What numbers did you get so far?
Okay, 1 second. With law of sines, I got 39.90.
Okay. Somebody else get that for law of sines? Jason too? Okay, how about law of cosines? What did you get? Come on, somebody punch it away. A squared equals b squared plus c squared minus 2ab cosine c. Oh, I haven't got 140 degrees. So how can we get 2 different values? What's the problem? So let's take a look at these 2 numbers and look at the graph. Look at the picture. Look at the schematic. Which one seems more reasonable? 40 degrees or 140?
140.
140, why?
It's off 2 seconds.
It's got to be obtuse. There's a large, this is the largest angle here, right? And if you do law of cosines, you wind up getting that. But with law of sines, you don't. So let's take a look at this. So this is the law of sines. I mean, this is the sine wave, right? This is 1. This is 1 and -1. This is 90, 180, 270, 360. So what you did on law of sines, you said the sine of A over little a, the sine of B over B, right? Angles are usually represented as capital letters, and sides are usually represented as small letters. So you wound up having, when you were trying to find something, you were trying to find alpha. Alpha was equal to the inverse sine of something. And what happens here, is what you're looking at is this or this. So there are 2 answers. And within a triangle, which a total number of angles, the total angles equal 180, you could get 2 different answers. But what does your calculator spit out? It always spits out the smaller angle. Your calculator will always give you the smaller angle. Now in the cosine function, 360. The calculator's also gonna spit out the smaller number. But in this particular case, when you're solving for it, it's the angle is equal to the inverse cosine of something, whatever it happens to be. And the value that you're getting is this value here. So your calculator can either give you this value or this value, because there are two values that equal in negative whatever. But your calculator gives you the smaller of the two values, which fits within the 0 to 180 range. So the deal is that whenever you use sine, you have to really be careful, because there are always two angles within the 180 that we're dealing with, because we're always dealing with triangles in nature, that it might give you the smaller angle, which is not correct. So this is one reason in engineering that we tend to use cosine way more than we use sine. Okay? So if you look over here, uses of sine, cosine. Cosine gives you the correct sign of the component. So when you go, when you say, you know, f1x is equal to f times the cosine of the angle of x, theta x, you're going to wind up getting the correct sign, because with the sine function, you have to remember to put it in. The third reason, do you remember dot product? In the packet, we just pulled a sheet out. In the packet, I have a sheet on the dot product. It's on page 4 of the packet. Remember dot product in math? I don't think the math teachers told you what it was going to be used for. You know how to calculate it. So there's two different ways to find the dot product, right? If I'm dotting vector A with B, I can take the magnitude of A times the magnitude of B and the cosine of the angle between A and B. Or I can multiply all the x's, the ax and bx by each other, add it to y's, add it to z's. In the end, when you do a dot product, is it a vector or a scalar answer? Scalar. So you get one value in the end. Take a look at this right here. If I dot a vector A, and I dot it with E, did you notice what E is used for? E is the unit vector. So in engineering, we tend to use E for unit vector. I think in math it might have been lambda. So E, for some reason, it seems really weird, but E is typically used for unit vector. Different texts use different things, but you'll find that I use E because the first textbook I learned from used E. So when you dot a vector with the unit vector, doesn't the magnitude of the unit vector turn out to be 1? Right, a magnitude of a unit vector is 1. So it's really A dot the unit vector x, which is really just the x-axis. I'm left with A, the magnitude of the force, times the cosine of the direction angle. Isn't that just like what we do when we do a component problem? If I'm trying to find the x component of a force, I multiply, I take it f times the cosine of the angle. Really what you're doing is the dot product. So when I try to find the x component of a force, what I'm really doing is dotting the force vector with the unit vector in the x-axis, and this cancels out to be 1. So therefore, fx is equal to f times the cosine of theta. In physics, when you had 2D problems, you probably solved fx is equal to the cosine of theta, and then fy would be equal to the sine of theta. You probably use sine and cosine just as much as each other in physics, right? But now that we're getting into more complicated problems, it's better to just use the cosine, because we're going to minimize the amount of error we might get, because our calculator gives us the smallest value. And that's problematic in the sine. But the bigger reason to use cosine is we're really doing a mathematical operation, which is the dot product, which involves the cosine of the angle between. And then if you look at the bottom, so if you want, well, actually, before we do that, let's look at this. when I took this force and I multiplied it by the cosine of this angle, the projection angle, didn't I just didn't I just calculate the component of this force along this line? So I take a force in any direction and I multiply it by the cosine of the angle, and I'm finding the component of that force in that direction. So in bicycle frames, Nick, just put your arm up straight somewhere, but connect somewhere to here. Like, let's say, yeah, that's good. So he's right on the origin. And it's important for me to know what force is being transmitted through this frame of the bicycle. And the force is here because somebody steps on the bike a certain way and they have a force. If I know the value of this force, the magnitude of this force, that's all I need to know is the angle between this and this. And I could find the component of this force that transmits through this frame. Does that make sense? So I could always use the dot product to find it as long as I'm dotting it. I got to dot it with the unit vector, right? Because I take the magnitude of the force and I multiply it by the cosine of the angle between. So I want this to be 1. So if I want to find the component of F1 in the direction of F2, do I dot F1 with F2? No. So let's do that again. If I want to find the component, so I have two forces. There's a force F1 here and F2 is here. I want to find the component of this force in this direction. Do I dot this force with this force? No. And mathematically, what am I going to get? What units am I going to get? Pounds squared. That doesn't mean anything. Okay? So I want to dot this. If I want to find the component of this force in this direction, I'm going to dot this force with the unit vector of this guy. Because I want the direction. So I'm going to dot this force with the unit vector here. Right? So I'm going to dot F1 with E1. So you want F1 dotted with E2. And if you want, you could do it this way. You could take the vector force, divide it by the magnitude, and isn't this just the unit vector? It's the same thing as the unit vector. Okay. All right, we're going to look at the syllabus on Thursday when I see you next. But just for some practice now, if you look on page 5, these are all the homeworks. And on page 6, which is where I want you to go, these are all the workshops. Workshops are like the PLCs. Physics calls them PLCs. I call them workshops. So the two that I want you to do now, and they're due on Tuesday, so it's a week from today. So what's today's date? No, actually, we're going to go into February, aren't we? What's next Tuesday?
Second.
Somebody check? It's the 3rd? So I'm assigning workshop number 2 and 3, and the workshops are on the web page. So if I go back, did everybody write that down? So they're due Tuesday, the 3rd. I'm going to switch now to the PC, hopefully. Trying to see where my cursor is.
Going to the other screen.
Go on to the other screen. This is all new to me, I'm doing 2 screens. Why is it just like flying across me and
Yeah, bring up the other projector.
You'll just have to trust me. The workshops are on the website. on the statics website. Okay, all right, so, I'll see you on Thursday. Evan's hours this week are Wednesday from 2 to 5, it's on the syllabus. No, I'm not assigning, oh, yeah, we should assign the homework too, that's right.
I mean, like, if you get them something.
Or yeah, like it's
There you go.
Okay, so, the resultant homework is due too, the same day. And then if you didn't turn in homework 1 and 2, you can turn it in on Thursday. Okay, see you Thursday.